record to this compute. Okay, folks, so let's start. You're right. After today, there will be only 3 additional lectures. So don't all cheer yet. So we're here, and I said don't cheer. Okay, so it's this one, and then it's these 2. We'll do instability today. By popular demand, we'll do computational, and I'll try and describe how you would create boiling water. What do we? I don't know what we're doing. We forgot to say what we're doing. Okay, there we go. So yeah, so today will be not necessarily a review, but putting into practice coding parts, because I would love to see you boil water. All right, that would be able to demonstrate to me that you understood what the hell we were doing. And, you know, as we'll see today, you can take any of these equations, and you've seen sort of the name of the game is to think about what approximations are valid, what regimes you're going to solve the problem in, the boundary conditions you're going to impose. These are all things that you get to create, and then you get to infer how correct your simulation is. So we'll do that again for these layers. Questions before we get started? Okay, wait, hold on, let's do one. Yeah. It's fine. Yeah.
I left the pencil here. I don't know if you have it. I like that pencil. It's one nice
Okay, moving on. Let me look at the SOTIs. If you haven't had time to fill out the SOTIs, please do so. I think 8 people. We got up to 8 people in the last one.
Nice.
Why is this not working? There you go. There you go. You got a little Italian now. There we go. So, 6. I misspoke. 6 and 6, 2 classes. So they close in 5 days. I know. Imagine not taking 5 minutes. 5 minutes. Just do it. Okay. Are we ready? Questions before we get started? What's that?
Is that like heat?
Lava lamp. Yeah, that's exactly what it is. Whoa. It's not really a lava lamp, but it's the idea of what a lava lamp is. So at the bottom, you have lava, and you heat up the lava, and it floats like real lava will. Of course, that's not really what happens. But magma does float to the top, right? Then heavier stuff sinks back down. Then it's heated to the back on. So this is the process called convection, right? Convection is the process of transporting heat by moving the material to a place where it can then get rid of it. In this particular circumstance, and what we'll talk about today, at the very top here, you have a cold boundary. At the bottom, you have a hot boundary. And if you look very carefully, you'll notice something quite cool. You look this over to the side, you see how it goes off like that? You say, wow, there's no like edge to the simulation. Well, on this side, I wrapped it. What's that? Whoa. Oh, shit, that's cool. Because you can do anything you want with the computer, yeah. Every time you rerun it, well, you would like play this and like a simulation. These fingers would fall and then go out again. The idea of chaos, right, comes from the idea of nonlinearity. And these equations are inherently nonlinear due to the fact that it's U del U. Anytime that you have the product of objects with one another, you end up with very nonlinear phenomenon and then chaotic solutions. Yeah, how long did it take for it to compile? Oh, a few seconds. Oh, yeah. You'll see today that it's very similar to the one that we did with the 2D advection. Okay. In every step, all we're doing is what I'm plotting here is the temperature. Okay. So we'll talk about this picture as a whole, but what you're doing is you have hot on the bottom, you have cold on the top, and that drives things like the velocity, that drives things like pressure, and that drives things like the density. And you have to relate all these things to one. Okay. Okay.
How do you wrap it around?
We'll get to that when we get to the
Okay.
Everyone's good at these, right?
Yes.
No one wants to review.
Another one.
Which one, this one?
Yeah, I don't remember. The next one.
Can we help him?
Yeah, who's ready to help him? No. You're always ready. You're always ready. We got you. We know you know it. That's right. Go ahead. Yep. Yes.
Next one is, I think that's the last one is
Close, like 97.9%. Let's give a round of applause. That was very good. Okay. So that was all correct up until this one. And the hint here is viscous.
Yeah.
Okay.
Wow.
That makes sense? That help, Paolo?
Yeah.
Cool. All right. This is the new one that we're doing.
Oh, shit.
Okay. So now you're going to notice that there are like italicized ones. This is ones that I think I remember from last time people picking already. If you pick that again, you have to pick that one and another one.
Okay.
If you pick one that's not italicized, then you only have to pick one. Late.
Yeah.
8 min. Yeah.
Can I pick one?
Yeah, you can go first. Go ahead.
I think gravity wave. Isn't that just how when there are two fluids, two different fluid mediums like air and water, right at the boundary of the two of them, that's what gravity waves look like. Because that's because of like gravity and buoyancy kind of like balancing each other out.
Good. So the only thing that I would add to that is, can you have a gravity wave inside of a fluid? Raise your hand for inside of a fluid.
I think so.
Raise your hand for not inside of a fluid. Only at the top of a fluid. Top of a fluid? Inside of a fluid. Can you have gravity waves inside of the fluid, or can you only have them at the interface between two? Which one? That one?
No.
Only at the interface. No.
Yeah.
Because that would get rid of the whole chapter on internal gravity waves. Okay? So remember that when we look at a cloud that forms after a mountain, let's say you have flow that goes over a mountain, and we saw that there are these waves that develop afterwards. Those are internal gravity waves, where just like you said, you have two forces at work. One is gravity and one is buoyancy, and they're resisting one another, right? They go up and down like that. That's where you get the Brunt-Väisälä frequency. Okay. All right, who's next? Yeah. Oh, this guy with the easy ones. All right, that's done. Anyone want to add to that? Cool. Let's go on. Yeah.
The caloric equation.
What's the caloric equation?
It's how internal energy and kinetic energy change in time and space. And
Good.
it's got on the right side, it's all the different ways you can change it.
Mm-hmm. Yeah. Anyone want to add to that?
I think
Okay, caloric equation, done. Yeah. Yeah, what's the continuum hypothesis?
Use macroscopic and microscopic quantities of the molecule in fluid, and it's only valid if the Knudsen number is less than unity.
Look at that. Let's go. And for folks who don't remember, what's the Knudsen number? Scaling. Yeah. So the idea here with the continuum hypothesis is that you have enough particles that you have many bumps into other particles before you have them move too far. So for example, the places where this wouldn't be true is like the top of the atmosphere. So the top of the atmosphere, a particle is going to travel potentially out of the system before it ever bumps into another particle. And therefore, the mean free path is too long compared to the scale lengths. Okay? Yeah. Yeah, go for it.
Reynolds number, and it describes how laminar or turbulent a fluid is.
Okay, I think we had that one last time,
I think
and I haven't italicized. Oh, here's what I'll do.
that one in Newtonian flow.
Oh shit.
Oh, shit. That means you'll have to pick a second one as well. Is that okay?
Yeah.
No, I'm not making it black. I'm
You turn off the screen.
Yeah.
Oh, God.
I think we also had caloric equation.
Yeah,
Yeah.
Did we?
Yeah, viscous as well.
Fisk?
also Newtonian fluid.
Continuity equation.
Where? Here?
Yeah.
Last time.
Dimension.
I have the Navier-Stokes.
Newtonian
Italicized.
fluid right below it.
Gravitational right now. Gravity wave.
Yeah, gravity waves.
Oh yeah, yeah, probably. Yeah, well then it maybe would have been.
Excuse me?
You're
No, bold is when they're removed.
Ah.
Then you can't pick them anymore.
Oh,
So we'll let them cycle through. So right now you'll have to pick, if you pick an italicized one, you have to pick another one
Okay.
as well. What's that? Because they're italicized.
All can you not see in back then? Because they are.
Yeah, just like tilted. Like the little lean, you know? Why don't you come up and do that while I run the class, okay? No, bold is when they're removed. I'm gonna leave them on, but you can't pick them anymore. Okay.
Okay.
All right. Having a day. All right. Who was up? You want to pick a second one?
No.
Okay. Yeah. Good. Anything you want to add to that? Yeah, Mach number, they are related to one another, but not exactly. Okay. Compressibility, good. We did that. Anything else? Yep. Okay, let's go. Right. Path line is the line that a fluid parcel follows. Kobe?
Oh.
Oh, you're screwed. Take it up with Paolo. You can do that one too if you want.
No.
Okay.
Isentropic is when there's no change in entropy.
Correct. Yeah. What's an example of an isentropic motion?
Adiabatic.
Is adiabatic isentropic? We have to look that up, don't we? All right, we'll wait that for next week. Well, if it's reversible, it'll be isentropic. If you put heat into it, right, may not be reversible, right? Because you can see the process of time. No, isentropic is reversible because there is no change in entropy. Isentropic. See ice, entropy. See the entropy right there, and then the ice right there. Ice O is the same.
Wait, so
Yeah, what does isotropic mean?
same direction. That's not fair.
What's that? Nope. That's isothermal. The same everything. Isotropic just means the same in every direction. Same. Okay.
Same everything.
I'm not going to change that here, but someone can pick that. All right, who's up next? Kobe, did you pick one? Okay, good. Yeah, what's advection? Okay. Yeah. When we think about advection, it's the process of moving stuff. Yeah. So typically we think about it as different from diffusion. So diffusion would be like leaking out from a source, whereas advection is like carried along by the right. Well, think about it. I like to think of it in terms of like rubber duckies on a pool. Okay. So let's say you're on a lazy river. All the rubber duckies are going together. That's advection. If you leave the rubber duckies on a pool and then they slowly just like spread out, that's diffusion. First time I've ever understood that. Thanks, Mateo. Okay, good. Okay, anything else? Yeah. Yeah, what's vorticity? What's that? Yeah, and what does it really mean for us, for the folks who you're explaining it to your grandma or... Yeah. Anyone want to help or? Yeah, how would you explain vorticity to your grandmother?
How spinny the fluid is.
How spinny the fluid is, right? How much spinny boy do you have in the fluid, right? Okay, and then you can always do this. This is a fun thing to do. Right? Yeah, very good. All right, so vorticity. Anything else? Okay, and what's specific about convection? It's not just circular. In fact, it's not always circular. There is rotation that's involved for sure, but it's a heat transfer, right? So it's a cooling process. Convection is inherently a cooling process. Okay. Now you might think to yourself, I have an oven that I put on convection, so that heats up my turkey, right? And you say, well, that is a heating process, Krismani. And I say, no, because the source of heat is the fire, and the fire is cooling down, but in the process of cooling down, heats up your turkey. So it's a heat loss process overall, but it just happens to warm your turkey up, right? You don't like that? Well, that is just how it is. So there's personal opinions don't matter. Anything else? There's a few people I think we haven't called on. Sean, ready?
Brains are caused by stress.
That's not a definition. That's a relationship. I do like that. But what do we mean by that?
So stresses are like due to like external force.
Right.
And then because of that, there can be like causes of strain depending on how much is done or like what we end up with from transformations. There could be like
I feel like you're nibbling around the definition, and I just want to make sure that we understand what the word strain really means for the fluid.
Like guess like the particle itself is like getting worked.
Yes.
Yeah.
So the parcel itself deforms, and the strain is the deformation, right? Which is different than the rotation. So stresses can do both. Stresses can rotate, and they can deform the fluid. Yeah.
The cause of the stress is something like rotating the like the pot that the water is in, or like moving your hand across the top.
Be very careful about the words that we just used. The cause of the stress is a force, right? The force causes the stress, which causes either a rotation in the fluid or a strain in the fluid itself, right? Okay. And that stress is communicated in the fluid by the viscosity, right? Okay. We're getting an intuitive feel here. Aaron? Which word do you want?
Which ones haven't been done? Is it
All the ones that are non-italicized. How can you tell?
I can tell different font.
Okay, I'm gonna need all of you to get glasses because I can see real good.
Maybe like
anything that's in
strike when it's over.
Oh, you want to do bold and strike? Okay, we can do that. So from now on, the italicized ones, and we'll just do this right here. You can ask if you want to do an italicized one. You're welcome to. You'll have to pick another one as well.
so the italicized are taken?
Well, someone has already done them. You're welcome to do them again.
A perfect gas to be modeled by the gas equation.
Which is what?
Big gas NRT.
What's that?
PV
PV equals NRT. Is there any other way to say that? Yeah, perfect. NKT? Or it's P rho KT? Whatever you want, right? What? Everyone done? Did I miss anyone? Giselle, I can see you. That means you have to talk.
Can you hear me? Can I'm gonna try shock. I don't know if I'm thinking of this correct. What happens when, say, like uh, aircraft goes faster than the speed of sound, and then you get that kind of like cone that comes out?
Yeah.
I don't know.
Yeah, so we actually haven't even really talked about it in class. So it's I'm glad that you're able to do that based on the small definition that we have. But the shock basically says when you're moving faster and the sound speed is able to accommodate.
Okay.
Good.
Okay.
Anyone want to add to that? Yeah. You're pretty shocked about that? Nice.
The fluid isn't able to communicate that you're coming at it.
Right, yeah. And it'll require you to have a compressive medium, right? So we'll talk about compressibility, I think, next week, but maybe not. I don't know exactly what the numbers are, but yeah, it's pretty close. You just have to start thinking about it much sooner than you think. It's not right at one. Okay. We're happy?
Base.
Front by solid.
Have we done that?
Yes, we have. It's just the gravity. What?
Yeah. What do you mean?
So you know how with gravity waves, how let's just use the example of like two fluid mediums, where it's like air and water, and you get like the collision of that with the gravity going to bouncing each other. The frequency of those waves created by the gravity waves, that's the growth by second. When it gets to that point where it's just like perfectly balanced.
Yep. The natural frequency of the medium. Okay. Cool. Ready?
Yeah.
So I just want to finish the discussion that we had about photographs. These are the Ekman layers that we were describing earlier. And we had essentially fluid that was being towed. What is the tow again? Stress. So wind was creating a stress in the U direction. And the flow was balanced by what? Coriolis force, right? So it's being pressed in this direction and it ends up pressing the flow off to the right, right? And that will go all the way down into the fluid. So as a function of depth, you can see the U and the V components are decreasing both in magnitude and direction. They're changing. And so we saw this in the solution itself because the solution had an exponential part that decreased with depth. And then you had a piece that was just a wave. And you can see the wave part here, right? This is going around in a circle. Right? Yeah.
What's the x-axis for B?
What's the x-axis for B?
Or whatever axis? The horizontal. What is that?
Oh, the magnitude of both U and V.
Okay.
So this is U in that direction, V in that direction. A photograph just basically tells you you're looking in both directions, and the path that's connected here is going to be the way that they're connected with respect to depth, right? The third independent variable. You've also seen these in the form of like, so you have a harmonic oscillator, and then you see like a U plotted against V, and they're called like phase space diagrams, or maybe X against V. Sometimes you'll see them that way. These ones are specifically both velocity components against one another, right? Okay. That make sense? Okay, that's all I wanted to do with these ones. They form an Ekman layer. It's basically a boundary layer in between these two fluid flows. Okay. So most people wanted to talk about how you do computation and working through an example like that. Okay. So this one will be basically how do we do this? Okay.
That's not a rhetorical question.
Yeah, how do we do that?
Well,
Boundary layers? No, there's no boundary layers here.
I think it means initial conditions.
There's no boundary layer.
What's the top and the bottom?
Oh, boundary conditions.
Yeah.
Okay. So let's set some boundary conditions. Okay, so first we need a box. Okay. And then what do?
We set grid space.
But make it hot.
Make it hot. So let's say that statement better. Temperature equals hot. Okay? Make it hot. Make what hot? Make the temperature hot. Okay, and up here?
Temperature equals cold.
Good. Okay, now what else? You really wanted to do the wraparound, right? How do I do that? You want to wrap them because that looks really cool.
Yeah.
What? Yeah, the left does equal the right. So this will require edge conditions that are very unique. But what you'll do is you'll just write that here is here. Okay. And when you do your derivatives at this edge condition, you'll go 1 over and it'll be over here. Okay, what other conditions do you have? What's that? That's great questions. Yeah.
You need to make a grid space or like find like the grid size.
Yeah, first we're still talking about initial and boundary conditions.
Oh, okay.
The additional fluid temperature on the inside?
Sure. So we could have some initial fluid conditions. Okay, so we could have like T at time equals 0 everywhere is going to be something. Yeah.
We need like the how it diffuses almost. Is that initial?
That's not really an initial condition. We'll talk about the equations in a few seconds.
So other initial conditions,
Initial or boundary conditions.
I was thinking like the viscosity of the fluid, or is that more so?
That again, with the diffusivity, those are examples of the equation.
Okay.
We need like how far apart the top and bottom is.
Yeah, that'll set your box length. We can talk about that in the simulation.
The top, the bottom.
No slip condition. Okay. So what does that mean?
Velocity 0 at the bottom?
Yeah, velocity is 0 along this boundary condition and through the boundary condition. But at the top. Same, right? You can't get out of the tub, right? So we'll have the no slip condition. Okay. Anything else? Or are we done?
So with the no slip condition, you just set the fluid velocity equals 0 at both top and bottom. Is that what it is?
Yeah, along this entire wall here, you'll set it every single time that it can never increase. I didn't say that. Oh, I just said at the bottom, we're going to set the velocity equal to 0. No slip.
Only the bottom or the top?
Top 2, yeah. What's that? Well, this boundary and this boundary are the same boundary now. So I wrapped it like it's a cylinder. So I can say over here, you know, this wall is this wall. Yep. Okay, so you'll need the density of the fluid. Now, you know, one of the things we can start talking about is what we actually need to solve this problem. Right now, I'm just thinking about, do we need any other initial conditions? So you're thinking to yourself, well, we need maybe an initial condition for the density, right? So we'll need something like, right?
Didn't knowing the temperature of the fluid give us the density?
That's a very good question. Very good question. So now we need to start thinking about the equations. We'll see if we missed any initial conditions or boundary conditions. What equations do we? Yeah.
Oh, so don't we need initial velocity?
Yeah, exactly. So you need U and V, right? Yeah, that would be all the initial conditions I would use. So what are the equations we need?
We don't need viscosity.
What's that?
We don't need viscosity.
Viscosities we're going to assume is constant everywhere. We would, if you can change viscosity, it's just annoying.
Would you use the caloric equation here?
You do need the caloric equation, right? Because let's think about what our variables are. What variables am I going to have? Not constants, just variables.
The variable is T.
T.
And we need time.
That's not a variable.
U?
What's that? U? Rho. What's that? It's not a variable.
Pressure?
P. Anything else?
Did John say G?
Yes.
Okay.
Why do you need position? Is that a variable? No, not. It won't vary, so it'll be a constant. So those will be our variables, and down here we'll have
the equations.
our constants. So we can put that and that.
Sure, that's mu.
What?
What's that supposed to be?
That's
Eta.
eta.
Okay.
Oh, wait, what is it? Is eta representing of this?
Oh,
stuff?
fine. We'll do this then.
How is mu?
Is that better?
I like
Better?
I like the more squiggly one.
Oh, you want the more squiggly one? You want this one?
Yeah.
That's a good view.
Okay. Anything else?
U
That's a
to
constant
X
G.
and Y. X and Y for the group spacing. Or?
Sure.
Wait, what do you?
These are constants. These are variables. Yeah. Yeah, it's right here. What's that? No, this is mu now. Anything else? Okay, we'll see if we need something else. You're missing something. We'll find out what it is later. Yeah. Yeah, so the volume is going to be wrapped up into this one right here. Right. Yeah.
So the top has velocity and bottom has position, right?
Top has velocities.
Yeah.
The bottom have the positions of the fluid. Why would the position of the fluid matter?
So you can do the calculations for equations.
Where? Where's the equation? What equations do we need?
Navier-Stokes.
Might need Navier-Stokes equation. Anything else? I heard caloric already. Right, yeah. So we might need a relationship between these. So as I start to write these out, right? I've written out these are the fluid equations. I'm not going to use them all. I'm going to use the ones that I need. I'm going to ignore the ones that I don't need. Okay. So I have some things here. I have 1, 2, 3, 4, 5 variables. To define this properly, we have to know the relationship between them all. And we have to model them all. Right? You just said something along the lines of, well, I have a relationship maybe between P and the temperature, or the density and the temperature. The thing is that if I want to use something like that ideal gas law, is that valid for water?
No.
No. No. But there certainly is an effect on the density, right? So you could make it up. Now you could look it up too, and there's real values. But you could say there's something along the lines of, I think that the density is a function of temperature. I think they're proportional. Yeah.
This one is going to be a lot like homework 7, 6.10, you said, right?
It'll start with those bones, yeah. Right? Okay. So you could say something along the lines of, I think the density is going to, how's it going to change with respect to temperature?
Decrease with higher temperature.
Decrease with higher temperature. So as T goes up, rho goes down. So that's an inverse relationship, right? Bada bing, bada boom. Does that make sense? Okay. You could use something as simple as this. And now you don't really have 2 independent variables, right? So now I've coupled these together. Oh, shit. Right? Good. So now I've reduced my dimensionality. So now I only need 4 equations. How many equations do I have? Yeah, I got 4, right? I got 1 here. That's the caloric equation. I got 2 here for U and V. And I got 1 here for rho slash T. Right? So I'm good. And then I had boundary conditions, so I can totally figure this out. Okay, so generally speaking, we need to make sure we have enough equations to solve the problem. We need to find out what our variables are. And then we need to think about how we would code this in the first place. So thinking about the process as a whole, on the left-hand side, I have mostly a T version and then a bunch of stuff. So let's start first with the continuity equation. I think that's written like this. right? So this is at a specific location, and this is summed. So I'll have to do that sum, right? But it's one equation. And on the left-hand side, I have a time piece, and on the right-hand side, I have a space piece. And I've done this intentionally to break it up, because this is going to hint to us computationally how to attack this problem. Okay? How do I do this piece on the left-hand side? Yeah. Just when I'm thinking about how to computationally attack this problem.
Approximation is like forward time.
Yeah, forward time is usually the standard way to go. Okay, so I'll say something along the lines of I'm going to approximate this. So I'll say rho at let's say t plus 1 minus rho t all over delta t, right? This is the approximation that I'm using. Yeah.
Would that be the left side? Just like only left side?
This is the left side, yeah. Yeah. And that would be equal to this derivative. Okay, I'm not going to solve that derivative yet. Okay, so now that I'm on this side and I'm thinking about forward time, I want to make it useful. So I want to know what rho is later. And that's always going to be equal to what my rho is now, plus some stuff or minus some stuff, depending on what the sign is. So I can multiply delta t to the other side, and I get an equation for t at a later time is equal to t plus some stuff, which you may recall looks a lot like right? Okay. So I could write here that this will be rho of t okay.
You need to find delta t now as a constant.
Yeah, so I'll need a grid spacing. So let's put that in here too. That's my time grid spacing. Okay. So this is already telling me something really important about how I attack the problem. Okay. It's going to tell me that I need to take time steps. Who would have thought, right? Okay. So that means that I'll need a for loop with time steps. Okay. Conceptually thinking about this, I'll need a time loop. Okay. And it's going to run my whole simulation. I'm going to start at the beginning. Advance by delta t, and then end at some later time. I don't know, whatever you want to call it. What?
Maxing t.
Yeah, maybe I'll do t equals something. Okay, there we go. Right? So that's the outer layer. And at every step, I'll have to do a bunch of things. I'll have to update the variables, each of these ones, at every step. So now I need to understand how they updated every step. So here I just found out how rho changes. Rho changes by this changing here. Okay. What else do I need to change? Yeah. So I have rho. Okay. I know how rho changes.
Oh, we need to know how you think.
I need to know how u changes, because in order to know how rho changes, I have to know how u changes. So what is the u equation that I can use? It's the Navier-Stokes equation, right? That is the generation and transference of momentum, right? So do I need all of these? What do I need here? Do I need these terms? No. Throw those away. I don't know. You could use, yeah, you could use something like this and say, oh, I just want the vorticity. Maybe. Is that going to be valid? I have to double check what equations I can use here, right?
I want the vorticity is the same.
What's that?
Place of the vorticity like doesn't change throughout.
The viscosity doesn't change. Vorticity is the rotation of the fluid. As I begin to heat up the fluid, it will start to rotate, will not?
Could we use the vorticity to find U and V?
Yeah, you could, right? You could relate this to the stream function. We've done that before. We did that in 610, right? So you could reuse that code to do this part. Or you could write these ones up, right? And I think for the purposes of showing you the ins and outs, you've already seen this one because you've done 610, right? Everyone?
I'm getting there. But I have done that part.
What is 610?
The coding?
Yeah.
610? One more problem?
It is the driven cavity with the vorticity and stream function.
Yeah, you drag the top of the fluid and the fluid rotates.
Yeah. This was actually 610.
Okay, so let's try this one. So we need to break it apart into pieces that make sense, right? So the left-hand side here, we're going to first divide by row. So all of these will have a one over row. And then I'm going to break apart that du dt into its components. So it'll look like this, but it'll look like that with respect to row. So it'll look like this. Right? And it's going to have this top piece. And this, of course, is where all the problems come from. I think it's like this. That divided by row is this, by definition.
The ones about I'm not what you literally just said about like the one divided by row. Oh, this. Oh, okay.
This is the dynamic viscosity.
Dynamic viscosity.
And this is the kinematic viscosity.
Okay, thank you.
They're just related by 1 over row.
Okay, thank you.
Okay. So when we look at an equation like this, we see the same type of format that we saw before. The other one, it was the time piece is equal to a space piece. I have to move this over, and then I'll have all the time pieces on one side and all the space pieces on the other side, right? And I can do the same thing. I can move that right over, and I'll have all my terms, and I can just calculate them. Because let's talk about the spatial terms for a few seconds. How do I calculate any of these pieces? I don't have to calculate that, right? You're saying the word time, but let's be careful.
Center space.
Center space, right? So when we do center space, we're just gonna take one of them, right? How do I do this?
Like E minus 1.
Yeah, so we have to remember we have a grid spacing, okay? And let's say I have this point here. This is I. This is I plus 1. This is I minus 1. Okay. Then I have the quantities P at I, rho at I, right? Maybe even U at I. Okay, and this is what I want. So I'm going to combine them, and I'm going to use information from nearby. So what's in between here? This is delta x. So I'll need that as well. Grid spacing. Okay. So I'm going to write this. How did you want to write this?
So PI minus 1.
I minus 1? That it?
Plus PI plus 1.
What about if I do that?
Two delta.
And?
Isn't it, plus PLI?
Plus PI. Row.
Oh, sorry.
So you need a row, right? So that's here.
There.
You're minus something.
Okay.
Right? So you do finite difference of all of these. You won't have to do finite difference here. That's what is G. Okay. You can do that here if you want to. You know how to do those derivatives.
Yeah, so for the P of I plus 1, do we have to use a different equation to get that before we do this?
Should I say that again?
So if we wanted to use the P of I plus 1, we have to use another equation before we can use this one?
Yeah, so you need to update the pressures everywhere, right? Oh, fuck. Okay, well now I need to find out how the pressure changes with time. Okay.
Is that a line of P or a row?
This is a row.
Denominator has a row.
It's the same equation.
This will tell us how U updates based on time. Do we have to do this again in the log action for V?
Exactly.
Yep.
Yeah.
And
Right? Because look, we have 5 equations, right? So we have to update them all. Right?
so
Yeah.
is it possible for us to tie pressure and temperature together like we did with row and temperature?
Yeah, that's a very good question. Very good question.
How else do we update pressure?
How else would we update pressure at every location? Yeah, so the relationship that we're going to have here, right, is going to be the one that updates temperatures and pressures, right? The pressures themselves are coming from the fact that the fluid has finite thing. You look in here, what do I have? I don't have T.
Yeah,
I have
sure.
E. And we haven't even defined that yet. Right? So we're going to have a relationship when we get to the caloric equation that directly relates these variables. Right?
Okay.
But what you're seeing is inside the time loop, right? You have a couple different steps. But every step, we'll go in, right? We'll indent one. We'll say, okay, first thing I'm going to do is I'm going to update the following variables. Okay? I know now that I'll need to update the row. I need to update U and V. I need to update T. I need to update P. Right? And then you just keep updating each one of those. So if you really want, this could be a definition. Right? You could say, okay, this piece here, which is just basically that, I'll give you, say, a variable for P and its 2 nearest neighbors and T, and I return the whole array, the updated array. Right? I hand you row, I hand you U, and you hand me back things. Same thing can be true here. So I might think to myself, okay, maybe I have a definition. U and row, and then it does that, right? But I'll have a for loop that walks through the entire array, and then another one walks through the other part of the array, updating row is equal to and then returning the updated array. Right? And I could do that with each one of these. We can update this one. Probably want to do these together. It's just copy and paste. Okay. And then these two, we'll have to talk about when we talk about pushing. Okay. I lost it. Okay. So now we have to do the caloric equation. Oh, that one looks hard, right?
Yeah. Are we gonna need a way to relate that internal energy to temperature? Or I'll just even everything like internal energy and the kinetic energy? Okay.
Yeah, so here we have this equation. We showed at one point that you could separate it, didn't we?
Yeah.
And that there were certain terms associated with each one. Like this, for example, did not work on the internal energy. It only operated on the kinetic energy.
Yeah.
Right? So we could write the internal energy somehow. How would you write the internal energy?
Is it which one? One of those two.
Second parentheses. Equal to the internal energy.
Yeah, sorry. Those are terms relating to the internal, but I'm just thinking about just the letter E. What's the energy in a fluid? Yeah, it's temperature dependent for sure. How does it scale with respect to temperature? Inversely proportional, directly proportional, directly proportional? Okay. Is it squared? Is it quadrat? Is it cubed?
I thought it was directly linear.
Is it linear? So is it just as simple as, whoops? Is it as simple as let's hope so. Right?
I think so.
T squared?
Like the higher temperature, the more energy is like bouncing.
Well, yeah, but then isn't that also the same as the relationship?
Yeah, equipartition of the energy gives you a coefficient in front, but it's usually always with respect to just T. Okay. The temperature is the driving energy force, right? So you can make an approximation like this. Okay, this is a simulation that you get to do. You get to set all the boundaries. So let's make a statement like that and say that it's just directly proportional to the temperature, right?
So when you say that, what do you mean in code? How do you do that?
Yeah, so we're gonna just replace that in our mind here. Okay. Yeah, you might do something here, and you might say, well, if I do proportional, maybe I'll make it equal, and I'll say something along the lines of I'm gonna make up a letter now. Okay. That's my new definition.
You just pick the value of it.
Yeah, you pick sigma for whatever you want. Amazing, right? Now we could look these up. These are all well known for water, right? But what I'm doing is I'm demonstrating how we could do this in a computer, right? Because what you're going to do is you're going to play with these parameters. If you wanted to turn off the internal energy, set sigma equal to 0, right? Then it doesn't communicate its heat at all. Okay. The reason that we're doing this piece at all is because what we know is in order to get the fluid moving, over here I have a dq dx, okay? Or a temperature diffusion on this side, right? So I'm putting heat in, and I'm changing the temperature, okay? You could also do this with, what's the name of the equation? I forgot the name of the guy, but there's the diffusion equation for heat, which you saw in computational, where you have a line and you heat up the middle and it diffuses outwards. You can use that code exactly for T, and you can avoid the caloric equation entirely. All Now we're showing you both of them here. You can make either choice, right? The nice thing about computational is you have some freedom, right? Now here you have these other pieces. What was this thing here? PDX. What's that? Yeah, so these pieces here, they operate on the internal energy or the moment or the energy itself, the kinetic energy. Yeah, these are kinetic terms. So we won't include them. We'll just have these pieces here, and then we can look at these ones. So here I have an internal gradient in the pressure on the velocity as a function of the pressure, and here I have some stress terms. Right? This would be your viscous dissipation force, be your heating force or your heating term, and then you have d e dt. Okay. Does that make sense?
If we separated the EDT like this, we did the first part, like du over dt plus and the base.
Yeah. So first divided by rho, right? This would be t over rho. This would be tau over rho. Okay. Yeah. Yeah, and then you need a relationship to go backwards. Of course, you need to be able to update your p's, and your p's are just going to be a function of your rho's, right? So let's say you've defined what your fluid flow is. You can have a statement about how do you relate these two things, right? So that's the relationship between T and rho. And here I have a relationship between the internal energy and the temperature. How do I set the pressures? Right? So the pressures are going to be set by our equation of state. So there is more to this proportionality than what's shown here, right? And then you're thinking, well, wait, did I actually get rid of one of these? Or do I need another equation? Right? Well, thankfully, I have my boundary conditions. My boundary conditions will come to the rescue. Will allow me to solve these with only 4 equations and then the boundary conditions. Okay. Have I lost folks? Yeah.
I still understand how she's getting pressure. Which one is the C?
We'll need a separate equation for pressure, right?
Based off of that relationship.
Where this will come from, yeah. Okay. It's a property of the fluid itself. We can pick those out. So let's say we want to pick water. It'll have one. So these typically have some form of, I put the proportionality symbol, but it'll have some sort of like length contraction or expansion. So it'll be like the density is some alpha that you find in a table, T, with some relationship with P. Okay. And then you update the pressures everywhere. So the way that we're looking at this entire simulation, is that you have update rho, you have update U, you have update V, you have update T and P. They're all coming along for the ride, and then they do every step. What we haven't talked about yet is that del squared part, right? In the spatial derivative, and we don't need to rehash this if we don't want to. When we did this, for example, when we did it in the 610, you solve at each time step, and then you solve the values inside of the box with the Gauss-Seidel method or with the over-relaxation method, right? And the reason that you know to do that is because you have something that looks like a Laplacian, right? You see the Laplacian operator, you know that it's not as simple as your finite differences because you need to take them everywhere, right? And you need to update the entire array to find the correct solution where it's smooth everywhere, and then you update it to the next step. Find the correction where it's smooth everywhere, and then you update to the next step. Does that make sense? Yeah or no? It is a lot. Yeah. Do it.
I was very sorry. So we will not be doing the finite difference for this location, or you guys are doing something really different.
No, this finite difference is for the first order right here. Right?
Yes,
And then you do finite difference for this too. But in order to solve it on the right-hand side, right? Put all the terms that are space-based, put them on the right-hand side.
Mhm.
And you have to continuously update the values until you get the right values. But that's the point of doing the overrealization method.
Okay.
Right? So in each one of these, if you have a Laplacian, it wouldn't be for this one, but it would be for these guys. Right? You'll have the same type of definition inside, where you have some sort of max iteration. You see that for the 610? Maybe you do it like 200 times at max, try and get it to some value. You have maybe a different definition. And you put in your initial values. And you solve the space to the right-hand side, and it spits out some new values below. Does that make sense or no? Yeah. Okay, not so much. We can come back to this on Wednesday.
Yeah.
And maybe it'll make more sense if we start to come back to it on Wednesday. You'll notice that we're missing some initial conditions and we see them now better. We need pressures, right? We need initial pressures. We're going to put these over here. Right? Anything else? Mm-hmm. It's something like a thermal diffusivity. You'll need that to get the heat into the fluid.
Oh, okay. And that's a property of the fluid that we choose?
And we'll pick that. We'll pick some
Okay.
number and then we'll play with it.
Gotcha.
What happens if you double the thermal diffusivity? All of a sudden, instead of convecting, it just diffuses. Right? It doesn't have to move the fluid. Right? Okay, I know this is very abstract. In practice, here's what it looks like. And of course, my code doesn't work, but I'll show you the exact purpose of it. What? That's an older picture. I just made this this morning. What? Yeah. So here, I'm just showing you the structure, right? The only thing that matters here is the structure. So you define the size of the box, you go through, you define some thermal viscosity, you define the temperatures at the top and the bottom. Oops. Then you initialize some of these. You'll notice there's not enough. Right? It's not working. It's the idea that matters. You don't have to take a picture. You know that I'll put this online, right? Okay. You have some number of steps, and then you have the things that I talked about. You update the time, and you have some definition, right? You have some old version, you update the temperatures, and then you set the boundary conditions, and you return the new temperatures, okay? Each one of these only returns the thing that I want, the U and the V, knowing all of the things that I started with. You'll notice that I got rid of the pressure one here. We'll talk about that more in detail on Wednesday, because I'm running out of time already. Okay. And then you go through I say easy, but it's not really easy, right? It's straightforward, right? Intellectually, all you're doing is you're advancing time. And the time parts and the space parts we're treating as separate. So time advances by dx, by dt, by dt, by dt, by dt, right? Whereas the spatial parts, as you see, the spatial parts as you see in here, I didn't actually include it in here. Let me just do this really quickly. Okay. So you can solve the Poisson equation using the Gauss-Seidel method. You walk through and you get the pressures to be correct. Basically, they have to be consistent. They have to be smooth, right? You don't have pressure discontinuities. And then you return the pressure and you update these values at every single one, right? So first you go and you update T, you update UV, and you update P, and then you keep the boundaries fixed. You'll notice there's not enough boundary conditions here, but you get the idea. Every time that you do these updates, T, U, V, P, does it matter what order you do them in?
Yes.
Trick question. It doesn't matter because hopefully your simulation will be happening at a small enough time resolution that the time difference is minuscule, all right?
Okay.
Now you'll see something like this time advancement part, right? And if you remember from computational, this is the simplest version of the time advance, right? What was the more advanced version, John?
That's a good question. Where are we finding about?
John always likes to shout it out, so I just wanted to see.
Oh. This is the simpler version?
Yeah.
Okay. I totally go with that.
Okay. It's the RK4, right?
Oh.
So if you want to do a derivative and you want to advance it in time, right? You would say on the left-hand side, you have some updated version of that value in time. It's based on the original value plus some small change in time and the amount that it's changing by. When we talked about our kinematic, here's our kinematic equation, right? So let's say I had V equals V naught plus delta T times A, right? This is essentially the same type of thing. So you compute the accelerations, you add a little bit of time, and you update the velocity. And we showed that you could do better than just this version. RK4 made some approximations, how you weight this material, and how you take a step forward. The same thing is absolutely true of the fluid, right? We are using the dumbest version possible. So inevitably, you will break it. Okay? Some of the fluids will be unstable when you treat them in different ways. And this is like whole branches of literature on computational fluid flow and how to do it properly, how to keep it stable over long periods. Okay? Yeah.
So we're gonna use RK4 or we use
No.
No.
What I'm saying is that this is the simplest version. I'm trying to draw this analogy back to when we just threw a ball and we simulated a single ball, right? You just take these time steps forward, right? Time step forward is the basis. Compute the accelerations. A is the right-hand side, right? Okay, we can come back to this in more detail on Wednesday. Thoughts before we finish? Okay. All right, break.